welcome back. It is your boy, Mr. Visca, math teacher extraordinaire. Well, I guess extraordinaire is more of a self-applied label, opinionated as such. But I am Mr. Visca, and I am a math teacher. That's factual. So, hello from Visca, the teacher. Yes, a little bit of self-promotion, doesn't hurt anybody. Anyways, let's take a look. This is the final lesson for the year for my AP Calculus AB class. Now, 7.3 is in the book. Okay, so this isn't Unit 7, Day 3. This is actually, we're going to do this in calligraphy because I like writing in calligraphy. This is Unit 7, Day 5, and this is the second part, so we'll call this Part 2. Okay, Part 2. If you look in the top left of my green bar, window bar, it says Day 5, Part 2, and the 7.3 is just in the book. It's Unit 7, Section 3, so it's 7.3 in the book. I don't give out the book anymore. This material is based on that book, the calculus book I use. But I give guided notes, fill in the blank type notes, and problems that are handouts. Okay? So don't be confused. This is Unit 7, Day 5, Part 2. I will break this lesson, this Part 2 lesson, into 2 videos. Okay? We are going to cover discs, okay, washers, all right, not shells. We're not going to cover shells. How come we're not going to cover shells? Mister, my AP Calculus AB teacher covers shells. That's nice. You'll see that the notes actually has a section on shells. But after a couple of years teaching this, I noticed that I never really saw a shell problem on an AP Calculus AB exam that I took. And I've done probably like 20 to 30 of them just for practicing myself, just for understanding what problems on there, whatever. And I never really came across a shell. I've come across a disc or a washer, but never a shell. So Unit 7, Day 5, Part 1 was slices. These are still slices, but they are in the shape of discs and washers. And these 2 videos will probably be broken up as such. I'll probably do video 1 is going to be discs, and video 2 is going to be washers. Okay? Let's get into it. All right, my boss at the Acme Rocket Company has assigned me to build a nose cone in this shape. Here's my shape right here, nose cone. All right. Suppose I start with this curve here. And by this curve, I'm talking about this curve right here, y equals the square root of x, okay? I start with that curve because that's how I want the shape of my cone to look. Now, I put a piece of wood on a lathe and they turn it to match the curve. So let's say my lathe is the x-axis. Okay, that means my shape is going to turn or revolve around that. So it's going to kind of come around. It's going to turn, and it's going to make a 3D shape, much like this here. You'll notice well, I tried to make that perfect, and I think I did a pretty darn good job. You'll see that's the cone. And as that spins around, all right, again, this bigger end spins around to here, comes back up, this, and then as I get closer to the nose of the cone, the circle gets smaller and smaller and smaller, all right? So that's what's going to happen when I rotate that curve that resembles y equals the square root of x. This is how we make things, okay? This is engineering. I would not advise doing this. Okay, number 1, playing with fire is bad. Okay, playing with fire is bad, kids. Okay, but never strap yourself. I mean, this guy, can he even undo these belts? I mean, look at how, I know I've got ADHD probably at some point. If you watch my other videos, you would probably agree. But don't do that. Don't strap yourself. I mean, what's this for? Can he really, target where he's going to land? I mean, I don't know, maybe Wile E. Coyote, that's his character's name. Maybe he's a genius and he's like, I think I want to land there. So if I just point toward the tip of that mountain, Don't do it, kids. All right. So here we go. We could find the volume of the cone. How? How could we find the volume of the cone? One way would be to cut it into a series of thin slices, flat cylinders. So you see how I've got this like disc, and that's ultimately what we're learning, the disc method. Okay, I've cut this disc out, so if I put my cone right back on the line, you'll see that it's almost perfect. Okay, you see the line from the x-axis, okay, to my function here. I'll do this in a green line. That is really the radius. Okay, that right there is the radius. All right, so if I cut a series of thin slices, which are flat cylinders. So trying to find the volume of a cone in general will be tough, but I can find the volume of a cylinder. I know the volume of a cylinder is pi r squared h. If I have the radius and the height, I square my radius. I multiply it times pi and times the height. Okay, so what if I just took all these cylinders I made that are stacked together to make this cone, okay, and they get bigger and bigger to the end. What if I got all these cylinders, all right, all the volumes, and I added them all together? Then I can get the volume of the cone. And keep in mind, okay, what do we use to add a bunch of numbers together? Integration. Okay, so just like Unit 7, Day 5, Part 1, where we use integration to find the volume through slicing, we're going to do slicing here, but this time they're flat cylinders or discs. Okay, that's where you're going to first see this word here. It's a disc. Some people write like disc like that. I don't know, was it right? It was written like this on the cover screen, wasn't it? I don't know. I always write it like this. But whatever. Now I got to go back to see. Yeah, look at that. Weird. Weird. All right, so we have this right here. Okay, now keep in mind, when I rotate this radius around, it's going to make that circle. Okay, it's going to whip around in a circle at the thickness. Okay, at that small thickness. So this is really going to be a 3D shape. Okay, it's really going to be a 3D shape, and that 3D shape is already drawn in the cone for us. Okay, now the height. Okay, it's the same thing as the thickness. Okay, so I'm looking at this disc, and if I throw a disc on the ground, if I have a coin, I don't put a coin on the edge like that. I mean, a nickel is thick enough, you can probably do that, but I throw a coin like this, right, on the ground like that. Here's the coin, that's a 3D version. The thickness is there. Okay, the radius is that. Okay, so my thickness would be this small change from there to there. And we're going to call that small change dx. That is a small change in x. Because if I look on my x-axis, okay, from this point, x value, to this point, that's a very small change. And let's not forget, in calculus, we call very small changes dx. They're almost like dummy variables in our integrals when we integrate. Okay, so this is dx, and I'll put the same thing down here. Okay, this little thickness is a small change dx for my coin in that cone. The radius is the y value. Now this gets confusing. Okay, it shouldn't be, but it is. All right, so I'll use purple. Right here, whatever the y value is, whatever y, that's my radius, because this distance is the radius. It goes from the center up. But how do we get y? We take the square root of whatever x is. So when I integrate, I'm not really going to integrate y. I'm going to integrate the square root of x. For instance, what's my y value here? Well, I take my x and take the square root of it, the square root of 4. So the y value is 2. This is the y value. But how did I get that? I take the square root of my x. So when I integrate, again, I'm not going to put the y in. I'm going to put the square root of x. So my radius is y. And in this case, we're going to use the square root of x because that's what y is. Y equals square root of x. Right? So therefore, if we add up all of our cylinders, okay, that's integration. That helps us add up a ton of things. Let's look at what we have. Okay? Let's look at what we have. We're going to integrate from 4 to 0 pi times the square root of x squared dx. Let me explain that one last time. And some of you guys are like, I got it, Visca, but there's always some that ask questions. All right? This was our volume formula, right? Notice the pi is on the out right here. We can always take constants and move them out. I always tell my class it's pi on the outside times the integration from 0 to 4 of the square root of x squared dx, okay? So we have my pi, and I'll use my highlighters. Pi is right here, or right here. My radius is y, but we're not going to use y. We're going to put the square root of x. So my radius is right here. And then we say h is just a small change in x dx. Okay? And oh, let's not forget, we need to square the radius. So whatever the radius is, don't forget to square it. That really is volume. Based on the lesson we did previous, in order to find volume, don't we just integrate the area? We do. We integrate the area. Isn't the area of a circle pi times my r, which is squared? This is the area. I'm integrating this. This is insignificant. That goes bye-bye. That happens to be the height for our volume. But I'm still integrating the area of a circle. Okay, I'm just adding them all up to get my volume. Okay, from 0 to 4. And I hope you realize our bounds are 0 to 4 because we start at 0 right here and we end at 4. All right? So I did a lot of explaining here. And really, sometimes I feel like when I explain a lot, I don't know if that complicates things more or not, because if people get it, and then I explain it another way for someone else who's having trouble getting it, and when I explain it that other way, sometimes people try and understand every single method. And you don't. If you understand one way to get it, you run with it. If you just want to integrate the area, run with it. If you just want to memorize any time we're doing volume of a circle or a disk, pi's on the outside, and whatever the equation is, you square it. That's it. That's in simple terms. All right? Let's go ahead and solve this. Okay, so before I do anything, I am going to simplify this expression. I'm not going to integrate it yet. I'm just going to simplify it. Okay, so let's go right out here. I got pi times the integration from 0 to 4. Well, if I square a square root, I just have x. Oh, now we're talking. Now it's easy. If I integrate x, that gives me x squared over 2. I want that from 0 to 4. And oh, by the way, let's not forget we're multiplying it times pi, right? So let's put in our 4 and 0. I have pi times 4 squared over 2 minus 0 squared over 2. Love putting zeros in. It makes things go bye-bye. And that's exactly what this is going to do. 4 squared is 16 over 2. So I end up with 16 divided by 2, which is 8 times pi. So I end up with 8 pi. That should be my answer. Now, let's check this in the calculator. If you do homework, or if you have a test where you have a calculator handy, and you need to show your work, you should still check it on a calculator. Make sure you didn't make a simple mistake. So I'm going to integrate just what we said here. Pi on the outside. Math 9. That gives me integration from 0 to 4. And I'm going to put this in just like we did without any simplification. I'm going to take the square root of x, and I'm going to square that dx. And I should get 8 pi, which I think that's 8 pi. But again, you have a calculator. So just check to see what 8 pi is. And that is spot on. Now, the calculus exam almost always rounds things 3 decimal places. This 2 would round up to a 3. So it is 8 pi, which is also similar to 25.133. Did they give us dimensions? Volume. They didn't give us inches thickness. Nope, no dimensions. So I don't need to put a label on there. Okay, 8 pi is exact. This is rounded. Okay, not bad. Not bad. All right. Here's where pulling it all together happens. All right. This is where, okay, this is the way I'm going to do it. This is how I'm going to remember it. If the shape is rotated about the x-axis, so let's say I have, just like we did right here, and we had a shape that's rotated around the x-axis, okay, for volume. So my volume is going to be pi times the integration from a to b of y squared dx. Now let me say something here. If it is rotated around the x-axis, that means you need your bounds should be x values. Okay? In the case of the cone we just did, it was from 0 to 4, right? So these should be x values. Okay? Your dummy needs to be dx. If you're rotating about the x-axis, your dummy needs to be dx. Okay? And last but not least, your equation that you integrate, the equation needs the x variables in it, which means you need x's everywhere. If you're rotating around the x-axis, you need x's everywhere. That's the easiest way to remember it. Your bound should be x values. You need dx. That means if you have dx, your equation needs to have x variables. So y is y. So how come? I'm not going to say y twice. So how come y is in here? Because in the problem we just did, wasn't y equal to the square root of x? So yes, we're going to put y in, but y is equal to the square root of x. So really, when I write this out, pi, the integration from when x is 0 to when x is 4 of the square root of x dx. So this, okay, don't forget, we got to square whatever that radius is. This in parentheses is your y in terms of x. Don't just throw y in there and integrate y. Okay, you need to use your equation, and your equation needs to have the x variables in there. It needs to be in terms of x if you're rotating around the x-axis. All right? So sometimes it doesn't rotate around the x-axis. Sometimes it might rotate about the y-axis, which means it would rotate this way. Guess what? All those rules apply. If we're rotating around the y-axis, you need your bounds to be y values, okay? You need dy, and if you have dy, your equation that you're integrating needs to have y variables in it, not x variables. Okay? So there we go. Notice, okay, volume equals pi times the integration of a to b. Now remember, these should be y values here. So I'm going to have some value a on the y-axis to some value b on the y-axis. How come? Because we're rotating it around the y-axis. We also need a dy. Again, y-axis, you need your bounds to be y values. You need dy, and your equation needs to be in terms of y, meaning you need y variables in your equation. This does not have y variables. This actually has the x variable. So in the previous problem, this is what I had. Okay, so I got to figure out what x is. I got to get x alone. They want 1x squared. Well, I got to solve for x here in terms of y. I square both sides. So y squared would equal x. Even though x is written here, I'm going to substitute my expression, which x is equal to with my y variables in there. That's a very bad y squared. So when I rewrite this, I would integrate this from, I don't know, a to b on the y-axis. Okay, multiply times pi. My radius is y squared. I still need to square whatever that is, dy. Okay, so that's the big thing, the takeaway. If you're rotating around the x-axis, everything's x's. Your bounds, your dx, and your equation needs to have x's. If you're rotating around the y-axis, then your bounds should be y values. Your dummy variable, dy, and your equation needs to have the y's in it. Okay, this is called the disk method. There's the K again, disk method. It probably is right, who knows? I just like a C, because I'm thinking like a floppy disk, you know, like a computer, like a disk drive. I don't know, is it a C? I don't know, it's, who knows? I teach math, kids. All right, let's take a look at this one right here. This is a good problem to do. This is good because now it's rotated around the y-axis, okay? How are we doing with time here? I've been doing a lot of explaining. Good, good. We'll finish this in the next problem, and we'll stop there, and then we'll do a second video for this last lesson on the washers. All right? The region between the curve, x equals 1 over the square root of y, from 1 to 4 inclusive, meaning 1 is less than or equal to y, which is less than or equal to 4, and the y-axis is revolved about the y-axis. So let's get rid of, and the y-axis got put in there twice, and is revolved about the y-axis. So this radius, this line, wherever it is, it happens to be here, is revolved around the y-axis. Okay? It's revolved around the y-axis. Find the volume. That is a cylinder. That is a circle. I'm going to integrate the area of a circle. Okay, remember in Unit 7, Day 5, Part 1, the volume was equal to the integration of my area, right? The area of a circle is pi r squared, so I'm going to integrate that. I am revolving about the y-axis. So dy, these need to be y values, my bounds, and my radius, okay? Whatever I'm squaring needs to be in terms of y's. I need y's in there. All right? So first of all, okay, this is a horizontal disk. If it's horizontal, it just means, look, it's parallel to the x-axis, okay? It's perpendicular to the y-axis. It is horizontal, okay? So we need our dy. I don't even look at it as horizontal or vertical. I look at it, if it's rotated around the y-axis, it's y. I guess the reason we say horizontal is because sometimes we might get one that's rotated out here. It's not exactly on the y-axis, okay? So I guess, yes, if it is horizontal, we use dy, all right? So the radius is x. Okay, but don't forget, we're not going to integrate x. What is x equal to? This. This is what we need to square, okay? So my x is 1 over the square root of y, and that's what's going to be my radius. Okay, that equals my radius. So if I just put that, if I put this expression right here, I leave the pi out here, and my bounds are from 1 to 4. We end up with the following. Pi times the integration from 1 to 4 of my radius squared dy. And the radius is 1 over the square root of y. So let's go ahead and do this. Another simple integration. You're looking at that like it's a fraction, Visca. My God, there's a square root, Visca. Don't worry. Let's simplify this part first before we even integrate it. If I square a fraction, okay, if I square a fraction, I square the top. 1 squared is still 1. And I square the bottom. If I square the square root of y, my square and my square root cancel, and I just end up with y. And this is a rule. Shame on you if you forgot it. Okay? If I integrate 1 over y, that's the ln of y. How come? Because the derivative of the ln of y is 1 over y. We're working backward. We're integrating. This is derivative. This is integration. We're working backward. Okay? I want that from 4 to 1. And oh, by the way, let's not forget we're multiplying everything times pi. Pi times the ln of 4 minus the ln of 1. That's a 1. Fancy. What's the ln of 1? I don't know the ln of 4 without putting that in a calculator. Let's get an exact answer, then we'll put it in a calculator, we'll check our work. The ln of 1 is 0. That's something you should definitely know. Which means I end up with pi times the ln of 4. That is an exact answer. But what is that approximately equal to? Well, that's what it is here. Turn this on. We got pi times the ln of 4. 4.355. 4.355 is the approximation of pi times the ln of 4. Now let's see if we're right. Let's put this in exactly as we wrote it down before we did any simplifying. How come I'm doing it before we do any simplifying? Because sometimes we make a small mistake when we simplify, and this is the only way we catch it. If we put stuff in before we did any work. Math 9, from 1 to 4 of, okay, I'm going to put a fraction here, and it is 1 over the square root of x. Okay, now I don't want you guys to freak out, squared dx. Why am I using x's instead of y's? Because the only variable that I put in is x in the calculator. Okay, so for example, it wouldn't matter if this was, okay, I'm looking right here, my equation here, my integration. If this was an r and a dr, in the calculator I would still put an x. If this was a t and a dt, I would still put in an x. So what if it's an r or a y? I'm still going to put an x in the calculator, so don't freak out. You'll get the same answer. Oh my God, I hope we do. And we do. 4.355. I mean, that's exact. Let me get rid of this blue writing here. That's exact. That's perfect. Well done. Okay, one more. How are we doing in time? Okay, got a couple minutes to do it. Perfect. This will be right around the 30-minute mark. We're doing good. Last one here. Now that's crazy to integrate. Not crazy to integrate. That is not crazy to integrate right there. It's easy to integrate. What's tough would be to calculate the answer afterward, okay? So the natural draft cooling tower shown at the left is about 500 feet tall. So in case you couldn't see, that's 500 right there, the top of it, okay? Here's 0, the ground. All right? And its shape can be approximated by the graph of this equation revolved about the y-axis. Okay, we're revolving about the y-axis again. That means we're going to need dy's. Once I see this, I'm automatically thinking, I need y bounds. I'm going to call it BDS, bounds. I need dy, and then my radius should have y variables in it. Okay, look it. Oh, it does. That's great. That is great. So this line right here is the equation. X equals 0.000574 y squared minus 0.439 y plus 185. Okay? Now set up an integration to solve for the volume, then solve using the calculator. All right? So our integration, pi on the outside, because this is obviously a circle or a disc, whatever. My bounds are from 0, which is the bottom, to 500. And I put this in as my radius squared. It's my equation squared. 0.000574 y squared minus 0.439y plus 185. This is my radius. Remember, I got to square the radius, dy. Okay, we're going to get an approximation here. Okay, again, that's a decimal right there. To take the derivative, I just add 1 and divide by 3, right? I just add 1 and then divide it by 2, the exponent. This one doesn't have a y. I'm just going to add a y there. Just to integrate, it's easy. But then I got to do it from 500 to 0. That's where it's going to get tough to calculate without the calculator. Can be done, but it would take some time. All right? So this is approximately. Put this down here so I can see what I'm integrating. Okay, let's clear this. We have pi on the outside. Boom. Math 9 from 0 to 500. Now, make sure you don't miss a 0 or a decimal place or anything, because this is an easy answer, an easy question to do, but it would also be real easy to mistype something in the calculator. So actually, parenthesis first because we're squaring this. 0.30, 1, 2, 3. 574x squared, okay, minus 0.439x, okay, plus 185. I'm going to close that parenthesis and square it, dx. Woohoo! That's a lot. Let's do this. Let's bring this out here. Good, we got an answer. Okay, so if you're an engineer, depending on how critical this is, depending on what the answer is, depending on who you give the answer to. Okay, maybe your high up boss, you give him a more precise answer. Maybe the guys you're working with, I look here, I got 3. It's about 24 million. Do they give us a measurement? Feet. So if it's volume, it's feet cubed or cubic feet. So it's about 24,732,567 cubic feet. Okay? Some guys you work with, you might say, oh, it's almost 25 million cubic feet. The guy who's relying on you to build this thing, you tell him 24,732,567.7 or 0.8 cubic feet. Just call it, maybe call it 68 if you round up. Okay, which we probably should have. It's better that way. Let's make that an 8. Okay. This is the calc test. Leave the 0.77 on there. That's it. We're done. Good job. We have one more video for the whole year. I mean, maybe we'll do some review stuff, but it's the last lesson, man. You've done a good job. Thanks for hanging with me, and I'm going to miss you when you're gone. We'll see ya.